Today we're going to apply some of our best Algebra 2 skills to analyzing sorting efficiency. We're going to concentrate on number of tests because that's what seems to dominate most of the efficiency issues. Let's start by reviewing the selection sort with that first sample that we did way back on the by hand worksheet. Our first test is the first two items, and we see that we need to swap those. Our next test looks at items. No swap necessary. 1 and 4 look good. 1 and 5 look good. So far we've made 4 tests and 1 swap, and we also know that the correct element is in the first element of the array. So now we'll look at elements 2 and 3. Need a swap there. Now 2 and 4. No swap needed. Now 2 and 5. And no swap needed there either. So we've added 3 more tests for a total of 7 at this point. And we also know that the first 2 elements of the array are in the correct place. So we can move down to element 3 and 4, do our test there, no swap. 3 and 5, also in good shape. So now we know that the first 3 elements of the array are all correct. That means we just have to check 4 and 5, which do need our final. So we end up with a total of 10 tests and 3 swaps. Now the program that we tested actually made 5 swaps because it's a little stupid at the end of each iteration here. But we're going to ignore that and concentrate on our tests. Now if we think of where that 10 came from, it came from 4 when we were looking to get the first element of the array correct, 3 when we were looking at the second element, 2 when we were looking at the third element, and then 1 to straighten out the last 2 elements. So for 5 items, n equal to 5, we found that we needed 4 plus 3 plus 2 plus 1 tests. Think about it for a minute, and you could probably guess that 6 is going to take 5 plus 4 plus 3 plus 2 plus 1, because we're going to need 1 more set of 5 tests to straighten out the beginning of the array. And in fact, if we have n items, it's going to take n minus 1 plus n minus 2 plus n minus 3 down until we get to the last 2, 1. Oh my goodness, that's an arithmetic series. It's an arithmetic series with a common difference of minus 1, a first term of n minus 1, a last term of 1, and n minus 1 total terms. Digging deep back into Algebra 2, we have a formula for figuring out what that is in terms of n. The explicit formula for the sum of an arithmetic series is n times the first plus the last over 2. Let's plug and chug. Substitute in for n, substitute in for t1 and tn, FOIL and reduce, and it comes out to n squared minus n all over 2. So if n equals 5, that's, let's see, 25 minus 5 is 20, divided by 2, 10. Just what we got. So summarizing, for the selection sort, we'll always see n squared minus n over 2 tests. And in fact, if you go back and look at the lab, we found 15 for n equals 6. And we found 1225 for 50. Check it out. The math works. Now let's look at the bubble sort. You can see the same kind of pattern occurring. We're testing going from the bottom of the array up to the top, but the same kind of principle works. It takes us 4 tests to make sure we've got the right guy in the first spot, 3 to make sure we got the right guy in the first and second, 2 for the first, second, and third, and 1 to straighten out the last one. Now we know the bubble sort can terminate more quickly under some conditions, but in the worst case, we're going to see exactly what we saw with the selection sort, n squared minus n over 2. The trickiest one to analyze is the insertion sort, and as we saw, it works pretty well. It's smarter in some way than the bubble sort and the selection sort. Let's see how it works. Well, there we actually start with doing one test to get the first two elements in a list in order relative to each other. So we do have to do a swap there because we want Bill to be ahead of Joe. And at this point we know that those two guys are in the correct order with respect to each other, perhaps not with the rest of the list. The next chunk of the insertion sort tries to make sure the first three are in the correct order, and you can see it takes us 2 tests to do that. Now we expand and try and make sure that we've got the first 4 in the correct order, and here we lucked out. The insertion sort only had to do 1 test, and because he knows that those first 3 are in order, we know that if we don't have to move Vera up over in Joe, that's the only test we have to do there. Now that's very dependent on that being a specific item that's already in the correct place. In fact, if you think of what might happen if it weren't Vera but Alvin instead, yeah, it would have taken us 2 more tests to get him to the right spot up on the top of the list, and a couple more swaps as well. So the same kind of pattern is asserting itself here in the worst case. It took us 1 test to get the first 2 in the correct relative order, 2 tests for the first 3, 3 tests for the first 4, and the same principle, 4 tests for all 5 in the correct relative order, although again you see that the insertion sort was smart enough to stop before it actually had to go and do those last 2 tests. So although in general the insertion sort is going to do better than the selection sort or the bubble sort, in the worst case, he too is n squared minus n over 2. So all 3 of those sorts are considered sort of order n squared worst case sorts. On average, the amount of time it's going to take to sort goes up by the number of elements squared. And if you think about the code for a minute, that's coming from the fact that we have 2 while loops nested within each other. The first one goes through n times, and the inner while loop either goes through n times itself, hence n squared, or in some cases a little bit less than n, so we end up with at n squared minus n over 2 in some cases. But the code represents that same kind of idea, n times n. Now that doesn't mean that some sorts aren't better than others most of the time. In fact, if you plot for random data, like we did with those 50 strings at the end, you can see that yes, in general, the insertion sort does better, and the shell sort that you can experiment with online does even better than that. But they all grow with the square of the number of items that we're looking at. We saw that quicksort, on the other hand, did a really good job, much better than those other 3 sorts in most cases. Your book attributes that to it taking a divide and conquer strategy. Now we've seen this idea of a divide and conquer strategy before when we saw the binary search. If we search a sorted list, 1 item at a time, going from the top to the bottom to try and find a match, it's going to take us n, or on average n over 2 tests to figure out whether an item is there or not. The binary search we saw, because it splits the problem into half every time, takes only log base 2 of n. Quicksort is essentially combining those 2 things. The divide, when it splits the array into 2 separate pieces, is a sequential process, and it basically takes n tests to do that. Now, every time it does that, it takes n, but the magic of it is it only has to do it log base 2 of n times. So if we do n things log base 2 of n times, we can see that it's going to operate much more quickly. In fact, it operates in general n times log base 2 of n. Now remember we said whenever we use logs in computer science, they're almost always base 2 logs. So computer people simply call that an n log n sort. How much difference does that make? Huge when you're talking about large lists. You can see that the x squared curve curves up relatively rapidly, even starting at 100, whereas the log curve stays pretty flat. If you take that even further out, and you look at 1,000,000 items, it's going to take 5 times 10 to the 13th tests for the insertion sort, for example, to succeed, whereas it's only going to take 2 times 10 to the 8 tests for the quicksort to succeed. Those still sound like big numbers, but let's say we could do one test every microsecond. If we do a test every microsecond, the quicksort will finish in a little less than 3 minutes. However, the standard selection or insertion sorts will be going for literally years. And I know what you're thinking. Quicksort was really complicated. Selection sort is easy. Some of us still don't understand how quicksort really works with all that recursion and subprograms and the rest of that stuff. Well, that's a good example of one of the trade-offs you're often going to find in designing and implementing algorithms. You can get better execution time, but very often it's going to come at a cost. The cost is either going to be memory, or in the case of quicksort, memory and simplicity. You can have execution time and simplicity and chew up lots of memory. You can have memory and simplicity and chew up lots of execution time. Or you can even sometimes have memory and simplicity and save on execution time. I call this the waterbed effect. If you've ever slept on waterbeds, you know what I mean. Push down on one side, goes up on the other side. Try and push that side down, goes back on the first side. Can be fun, but you can't get it all down at the same time.